So welcome to lecture 11 of MCS 471, an introduction to numerical analysis. Today we continue to solve linear systems. So we have so far introduced the matrix notation, the matrix norms and conditioning. We have seen last lecture row pivoting for solving linear systems, and today we will consider iterative methods. Actually, we will consider two iterative methods to solve linear systems. Why do we do this? Well, in many occasions, we already know the location of the solution. And in many situations, the linear systems are also rather large. So using an iterative method can, in these circumstances, in the circumstances when we actually already know an approximation for the solution, a low precision, in a low accuracy, if we have already some estimate for the solution in that situation, and when the number of equations is rather large for direct methods to apply, then iterative methods can outperform the LU factorization. So we will see that in the cost of the methods, that the cost depends on the speed of the convergence, and it also depends on the number of steps we have to do, and then also in the cost per step. So if things go well, we may end up with an algorithm that is converging that actually requires that is converging well, and also that where the total number of cost is quadratic in the dimension. So that's kind of the global overview of this lecture. So let us derive the formulas. So we worked with iterative methods before. So when we derived iterative methods to solve one equation, we were working with fixed point formulations. Also here, we are going to rewrite our problem as a fixed point problem, trying to reduce the problem into a simpler problem. Well, from the LU factorization, we already know that solving lower triangular and upper triangular matrices has a lower cost. So we will split off the lower triangular part, actually the strict lower triangular part. Then we have the diagonal part and the upper triangular part. So this decomposition, so writing the matrix as a lower triangular matrix, the diagonal matrix, and the upper triangular part, allows us to rewrite the original problem as a fixed point problem. So here you see how this goes. We actually are trying to isolate the diagonal. So actually here we have already our fixed point problem. So solving a triangular system is fast, but actually solving a diagonal system is even faster. And here I should have pointed out right away that because we are isolating the diagonal part and we're going to solve a diagonal system, the elements on the diagonal better not be zero. So the methods will work, but they will work with some conditions. And the first condition is already that the elements on the diagonal better not be zero. If one has, and actually they better be large as well, as we will see later. if we do have small elements on the diagonal, well, we can always interchange rows like we did with the row pivoting. So we have our fixed point problem that is already here underlined. We rewrite this a little bit differently. So we're going to, since the diagonal matrix, so the elements on the diagonal are all non-zero, we can explicitly write its inverse. So normally we don't really do this, but the inverse of a diagonal is just taking the inverses of all the elements on the diagonal. And with this formulation, we have actually not only a fixed point formulation, but we can also, you can see we can write the next element. So we can write at the fixed point, we actually have that the b minus ax equals 0. So we actually have the update that we have to do. So perhaps I will now switch to another color. So in blue here, this will be the update factor. And the update factor that we need to do as long as we are not yet at the fixed point. But you can see that the update factor is actually correlated to the residual, the b minus a times x. So we are solving here a times x equals b. So you can see that if we have a converging method, the forward error will go closer, smaller and smaller, and that's here closely related to the backward error, the residual. So we have our fixed point formula that is again well defined if all diagonal elements are different from 0. And that gives rise to the first method we consider. That's the method of Jacobi, or the Jacobi iterative method. So here we have a delta x that we add to the solution, the delta x that is actually obtained by taking the residual vector. So we are already somewhere close to a solution. So what we do is we check how close we are by computing the residual. And then we compute the update by dividing every component of that residual vector by the corresponding diagonal element. So that is the iterative formula here, so that we run and that we apply in an algorithm. So in all iterative algorithms, they may not converge. So we have an upper bound on the number of steps. And we also have a tolerance on the accuracy. And actually here, because the delta x is so closely related to the residual, we have actually only one tolerance. So the stop criterion consists in us checking whether the norm of the update is small enough. So if we have a converging iteration, then that norm will actually be a very good estimate for the accuracy of our solution. Okay, we have a fixed point formula, an iterative formula, and now also an algorithm. Let us first look at the cost and the convergence. So here it is both the cost and the convergence all lumped together in one slide. Why could this be better than, for example, LU factorization? Well, remember that the LU factorization is a cubic operation in the dimension. So it's n to the power 3. Here, if we look closely at the costs, what is it that we do most? Well, actually, the matrix vector multiplication is actually the portion where we have to spend most of our time. So most of the effort is actually in the matrix vector multiplication. All the other operations are linear in the dimension. So there are other operations here. So the minus is a subtraction of two vectors. The plus is also a vector addition. So the other two operations that are here, the minus and the plus, are linear. And essentially also the multiplication with the inverse here. This is not a matrix multiplication, not a matrix vector multiplication, but that is executed in a scalar fashion. So the cost per step is n square, and the total cost depends on the number of iterations that we are willing to do. So you can see that if the little n is much larger than the capital N, so if we have that the little n is much larger than the capital N, then actually we do have a better algorithm than the LU factorization. So it can be a significant reduction in cost, especially when you have many equations and many variables. So what mattered with the LU factorization was also that we picked somehow the largest element on every column. Here actually also matters is that we have a matrix where the diagonal elements are actually dominating. So the elements on the diagonal are larger than here the sum of all the elements that are of the diagonal seen row-wise and seen column-wise. So this is what it means to be a diagonally dominant matrix. Now this seems to be a rather restricted class of matrices, but we will see when we get to partial differential equations that diagonally dominant matrices actually occur quite naturally in the discretization formulas. So diagonally dominant matrices are actually occurring naturally in certain settings. Also, we know how to do pivoting. So you can actually scan a matrix and do some row changes and column changes so that the largest element occurs always on the diagonal. So that also actually allows you to pre-examine before you start running the iterative methods, examine whether the method has a chance of converging or not. But actually already your residual will tell you that. I mean, if you are too far from the actual solution, then your residual will be too large. So your delta x will be too large. So in any iterative method, we didn't really say this, but whenever you start to diverge, you actually also better stop. That's another issue that we haven't touched on in the first chapter. All right, so let us now define the method in a Julia function. So we had pseudocode, but let us now look into the specification. So we have on input one matrix and a right-hand side vector. And here it said a solution, but it's an initial approximation for the solution. So we call it also a start solution. So that's the first initial guess that we have for the solution to the linear system. For the other two parameters, we do have our n and our epsilon for in the pseudocode of the algorithm. We provide default values. So the method may converge, but may converge rather slowly. That's why we actually have 100 elements. And actually, the tolerance might actually be quite high here, 10 to the power minus 8. But we will pick nice examples. So we can construct diagonally dominant matrices. That's what we will do when we test this Jacobi matrix. So you see the documentation. So the method will fail, may fail if we do not reach the accuracy in the required number of iterations, in the allowed number of iterations. So let's now look. So here you see the prototype at the very bottom, again repeated. And let us look at the algorithm. We will adjust the solution. So here I make a deep copy. So otherwise I may lose the start solution. So that could be inconvenient if we are comparing methods, what we will be doing. Then the method is actually summarized in this loop here. So we, for once, we don't use a for loop, but we use a while loop with an explicit iteration counter that is initialized to 0. We do the computation of the backward error, so we compute the residual. So this will here be the most consuming step, so it's kind of deceptive, it's in one line. And here then we do the division by the diagonal elements. And as the third step, we update our result. So the method is verbose. It actually is printing the norm of the update, so we can track the progress of the convergence. And if the norm of the update is less than or equal than the requirement on the accuracy, then we leave the loop and say that failure is false. All right, so there is a main function, and with the main function, I want to indicate that we are making the matrices diagonally dominant. So we will generate a random matrix, and we multiply all the elements by 100. So the dimension is prompted. So this is a main program to run at the terminal command prompt. I will post also a Jupyter notebook where the main is actually replaced by a number of execution cells. We will make a system where we know the solution. So the solution here consists of ones. And we will also add some noise. So we make some noise here. That means that we have to start from somewhere, so we can actually regulate how close we are starting. So if we are testing a new method, we just don't test it on any problem, but we make sure that we are satisfying the requirements. So the requirement being here that if we want convergence, we have to start close enough. So here we want to reach 10 to the power minus 8, while we start at 10 to the power minus 4. So we have about 4 decimal places correct in our first start solution. So we will make our first start solution by adding the noise to the exact solution. So the solution is exact because we have computed the right-hand side explicitly as the product of the matrix with the exact solution. All right. Then we print our matrices. Perhaps I should have pointed this out earlier. So we print our matrices by this show function, where we are fixing the number of decimal places to 3 after the point. So that means that our random numbers, we can look at them, that they are actually looking good. So the solution, of course, is printed to the full accuracy of the 16 decimal places. So this is the main program that is replaced in the Jupyter notebook by a number of cells. And here we have success. So here you see our random matrix. Notice we printed out because actually we have indeed a diagonal dominant matrix. Look at the exponents. So the exponents are +1, so they are all of the size 100, so 200, 300, 700, while all the other elements are less than 1. So we have actually, you could say that we have a matrix that if you would look at only the first decimal places in a regular notation, then actually indeed you would have a matrix which is close to being diagonal. So you could also see this, that the method of Jacobi works well if your matrix, we called it diagonally dominant, but if your matrix resembles a diagonal matrix really well. And this was really a good iteration. So here you saw that we were converging quite fast. The convergence is still linear here. So it's not quadratic converging method. So we do have a constant number of decimal places in each step that we gain. So you could say that we gain 2 decimal places in every step. So the convergence is still linear. So we started with 4 decimal places, and now actually you see that we do have 10 decimal places accuracy. That was because the tolerance was 10 to the power minus 8. All right, so this is our first method. So let's run the method of Jacobi. And let's do this for increasing dimensions. And the first part of the exercise requires you to reason. So after a certain value for m, the method will no longer converge. And why is that? Well, as you have more and more numbers, we multiply it with a fixed 100. So here the critical statement is actually the 100. And one can expect, so the numbers in a random number generator are between 0 and 1. So one would not expect for values of m less than 100 to be troubles. But as soon as you cross the threshold of m equals 100, then actually it could be that, and especially when you have a diagonal element, which was also random, which was rather small, then actually it could be that your matrix is no longer diagonally dominant. So if you know the m, and of course we always know the dimension of our matrix, then actually we can adjust. So that's then the second part of the experiment. We can actually adjust the 100 here so that we always converge. So the 100 and the m then actually be rather the same. Or you could say that if you're already starting to cause troubles for m 50, then you could take the twice the dimension. So the purpose of this exercise is mainly to reason about what it means to be diagonally dominant for a matrix. It's also to work with this run Jacobi here. So I still typically run most of my Julia programs at the command prompt. Occasionally also at the within a Jupyter notebook. So it's also an exercise for you to see the relationship between a main program and a good, well-designed sequence of execution cells. Where here you again have to insert some loop. So the main in the run Jacobi is iterative, is interactive. It will prompt you for this dimension. And that prompt is very unnatural in a Jupyter notebook environment. All right, then, here is now our second test. And that second test system will actually be the motivation for our second method. Our second method will converge much, much faster than on this system. So you see, on this system, the matrix is still diagonally dominant, but barely. So we have a matrix of dimension n, so n rows, n columns. All the off-diagonal elements are 1. So if you sum up the off-diagonal elements, you get n. Well, then you get a diagonally dominant matrix adding 1 to n. So this is kind of a lazy diagonal dominant system. So it's almost not diagonally dominant. So what you will observe here, and you will change the default tolerance to 10 to the power minus 4, otherwise it would take a little bit longer. You will actually examine how many steps you take, and you will also take sufficiently many iterations. So here, I mean, a dimension that is sufficiently large. So in the previous exercise, you kind of went to up 100. Also here, don't hold back. Well, if you take 100, let's take n equals 10. So that means that n will be 200. So how many steps does the method of Jacobi take to converge? So we will repeat this exercise then when we see the next method. All right, so the next method is also an iterative method. It's called Gauss-Seidel relaxation. And it starts on the same way, so with the fixed point formula. We actually can relax now our condition that the matrix is has non-zero elements on the diagonal. So we have a different fixed point formula. So what we did with the first iterative method, we reduced our problem to a diagonal matrix. Here actually we reduce our problem to solving a lower triangular system. So solving a lower triangular system is actually that we can do already. So that is our new iterative method. It will be a more complicated method, slightly more complicated, but the work will pay off. So we will have a faster converging method. And actually you could interpret the method so that we apply forward substitution in each step. Now the formulas look then a little bit strange if you think that way, that we apply forward substitution in that way. But here there is another way to look at it. So if you forget about the fixed point iterations for a while, actually we start with the method of Jacobi again, but now we write it component-wise. So what we do is when we run this method, we run this for I that is increasing. So if we do this for I equals 1, we actually already know when we compute the second component for I equals 2, we actually have a better value for the first component. So let me repeat this. So we are updating this vector now component by component. That was what we did with the method of Jacobi, but we split it off the residual vector because that was our convergence criterion. So the idea is actually if we have already a better value for, say, the first component, then we may already, it would be better if we already use that value when we compute the second component. So that leads to a rewrite of the formulas. And that will actually define the method of Gauss-Seidel. So what we will do is we will split off this big sum here. So you see the J in the big sigma runs from 1 to n. Now here we have the big sigma that starts from I instead of 1. And here we have the stopping criteria, that is 1. That is I minus 1. Where in this first sigma, we are already using the improved values to update. So that will lead to a significant improvement in the convergence for certain systems. Here is the algorithm written in pseudocode. What we still want the delta x. So the formulas were mathematical formulas. So we could do them component-wise, but the formulas there are actually not really leading into an algorithm with a stopping criteria. So here we have the stopping criteria that the norm of the update should be less than our desired accuracy. So we are going to compute this delta x. So here we essentially rewrite the update formulas, initializing with the right-hand side. So that's one initialization of vectors. Then we have the first update, where we use already the new values. And then we have the second loop. So observe also the end points here and the beginning points there, where we are using already the new values in the first loop. So it's still a mathematical algorithm because we are essentially using the superscripts, the k plus 1 here. So, and in a way, this formulation is actually still incorrect because you see that we do the update only at the very end. So it's still an incorrect algorithm, but it is trying to get to our delta x. So actually the update here, this update in the correct algorithm should be interlaced. So as soon as we have our delta x, we actually do the updates. So what is changing now is that actually the delta x gets computed differently. So the delta x here is computed based always on the latest results. So we have this update of the delta x, and here you see that we are already updating the results. So what I indicated in the pseudocode algorithm, what was wrong there, is actually fixed here. So this is the loop where we update also the delta x immediately, where we update the result immediately. So the update, the calculation of the update and the update of the solution happens at the same time. So it's not done at the same moment as on the previous slide. So the previous slide served as an introduction, as a transition between the formulas and the actual implementation. So in this course, we define our algorithms with Julia functions. So this is the definition of the Gauss-Seidel method, not the pseudocode of the previous slide. All right, so and then we run this on the same input. So to be rigorous, we fixed the seed here. So you recognize again the same matrix as before. Notice that it is a diagonally dominant matrix, and we have 700, 300, 200 as kind of the values on the diagonal. And of the diagonal, we have much smaller numbers, numbers that are smaller than 1. So here you see the largest number is 0.9. So this is a nice diagonally dominant matrix. And when we look at the progress of the error, then we see that it already stops after 3 iterations. So in a way, we are only saving 1 iteration. But in the next example, it will be more dramatic. So here you see that we are converging faster, so we have to do less work. And actually, if you remember, we actually also get a little bit more accurate result. So here you see that this looks more accurate than the 10 to the power minus 10. Okay, we actually have the same cost, so we are doing matrix vector multiplication. We also have the same condition on the convergence, which is reiterated again. So if the matrix is diagonally dominant, then it will converge. And here there is an or, so I should pointed this out earlier. So it suffices that you do, if you want to interchange to the largest elements, you don't have to do both row pivoting and column pivoting. So, but what we have experienced is also true in general, that if the method of Jacobi converges, then also Gauss-Seidel will converge, but Gauss-Seidel will in general converge faster. It will still converge linearly. It's not a quadratic method. All right, so now comes again the test system of exercise 2. So that system was almost diagonally, was diagonally dominant, but barely diagonally dominant. So we just added 1 to the diagonal. So for that, the method of Jacobi was actually converging very, very slowly. Here you will see that the method of Gauss-Seidel actually converges significantly faster. So that's kind of the computational selling point for this method of Gauss-Seidel. All right, can we still do better? Well, it will turn out that we can. So Gauss-Seidel is also called Gauss-Seidel relaxation. You kind of relax the problem of a full matrix to a lower diagonal matrix. Now with over-relaxation, we can kind of overcompensate. So the main difference between Jacobi and Gauss-Seidel is that you are already using the better approximation for each coordinate, while you can try to do it a little bit more, so you actually give more weight to the previous better approximation. So there is a weight, a relaxation parameter, omega, or W if you like, for weight. We have an over-relaxation if the omega is larger than 1. Less than 1, we have an under-relaxation. So it's actually good we have a parameter to play with. And we can see this method also as a fixed point iteration. So the formulas again start from the decomposition, so the summation of the matrix as a lower diagonal part, a diagonal part, and an upper diagonal part. But now we introduce this weight, and you can see we multiply through, so we actually get the same equation. We turn this into a fixed point problem where we move the upper triangular part to the right. So we do just the same as with the Gauss-Seidel. We will actually have a lower triangular system. So you could see again this as a lower triangular system, but now with a parameter. And rewriting this, we kind of used a trick. We added the diagonal and we subtracted the diagonal. So here you see the diagonal coming in here, and the diagonal comes also in here. So it's also an indication for the fixed point again. So in a more explicit form way, we can actually write this method in this form, but it's actually not such a good form. So if you would see the update, it's actually better to do the previous formula, the formula that is over here. So this is a generalization of the method of Gauss-Seidel. So when we have the parameter equal to 1, then we have Gauss-Seidel again. You could also see this that we kind of interpolate. So we kind of do a weighting. It's also kind of giving a weighting that is interpolating between the diagonal and the upper triangular part. So with the 1 minus the weight and the minus the weight. So if we over-relaxate, we actually give more importance to the update, and that is expressed over here. So the over-relaxation is done here by the default 1.1. So this is a new default value for a parameter. So a new parameter, we give it a default. So the method is very similar, except it's very similar to the method of Gauss-Seidel, except that we have the weight parameter in two places. So we have the weight parameter when we multiply the right-hand side, and also when we update with the result. All right. So we covered the method of Jacobi because we can recycle a lot as in the function of Jacobi. So that's Jacobi was a very simple method and was actually quite nice to implement. Here we can now focus on what really matters. All right, so I copied this special matrix from the textbook. So this is a matrix that is actually kind of diagonally dominant, but it also has a very special structure. And the structure, I can tell you, looks very similar. So it's actually a tri-diagonal matrix, but then there are also there are a lot of zeros, but then there are also kind of strange anti-diagonal elements. So what we see is that this is a special matrix where we have the diagonal that is larger, but slightly larger. We no longer have these huge magnitudes. So also some issues with the definition of the matrix. So we start actually from a list of numbers, and you can reshape a list of numbers into a matrix. So these are two operations that are often very useful when you want to make your own matrix, starting simply from a list of numbers. All right, you see that we do have convergence with the successive over-relaxation. You kind of see that the method converges, but actually rather slowly. As I go here, now you see that it takes actually 3 decimal places to gain, 3 steps to gain 1 decimal place. So the method is converging, but rather slowly. But this is a different problem. But it converges after 9 iterations, and we also have about 9 decimal places correct. So this was a very fine example for the successive over-relaxation. Why do we do this? It looks like a complicated idea. Well, you will find this out. So if you are going to run the methods of Jacobi and Gauss-Seidel on this special matrix, then you will see that successive relaxation is actually better than the method of Jacobi and Gauss-Seidel. So the answer is obviously yes to this exercise, but you will have to provide the motivation, to provide the computational justification for this, why this is turning out better.